Okay, so today is going to be a revision lecture. So I'm just going to basically go through anything that you guys want me to go through. I sent you also the sample midterm. I hope you all got that right. You managed to download that? All right. So is this the same as what you got?
Yeah.
Okay. All right. So the first question is to evaluate expectation values of this thing. Yeah, so evaluate expectation values of X, Y, and Z. Now, basically, for this one, what we'd be doing is to just use our formula for the expectation value. So we just have to sort of evaluate from X, this thing, and we can actually, so when we did it sort of for the composite system one, we more use this bracket type notation, but we could equally use just the matrix kind of notation. So in this case, you would write this as sine X and then minus cos X. So this is, I think, where in the homework, some of you were making just a calculational error because you were not taking the complex conjugate of this term. So, and then this one is a column vector sine X, and this is a plus cos X. And then, so sine X minus I cos X. Basically, this one will flip the ordering of the two terms. And then when you calculate this thing, then you're going to have a I sine X cos X. And then this one will be minus I sine X cos X. So this one will actually be 0. I think for this one, what you should find is that we could actually visualize this thing. Right. So if you go through and do the same thing for Z, so you need to visualize this thing eventually on the block sphere, right? So for Z, let me just do some mental arithmetic. And so I think this one is going to be, I think, sine squared X minus cos squared X. And then for Y, okay, for Y, I can't do it mentally. So, but let me just skip a few steps and then I think, so this one will be, oops, sorry, not what I meant. So, oops, so this one is sine X and minus cosine X. And then when you multiply this Y by this vector, then what you should have is, so this one, sorry, this is multiplied by, the vector should be cosine X on the top and then I sine X on the bottom. And then the final calculation should be, so sine cosine X, and then there's two of these ones. This I here, and then this minus I here will give +1. So these ones will add to give 2 cosine x, which is of course equal to sine of 2x. This first one is actually minus cos of 2x, right? Okay, and then so basically the block sphere, you basically use these things as kind of coordinates, right? And so what this already tells you is that on the block sphere, so because expectation value of x was 0, so when you plot this, this is z, and then this is, say, x, and this way is y, right? So because x was actually 0, so what this actually means is that it's actually somewhere on this circle, which is in this zy plane, right? Because z and y are non-zero, and so depending on the value of x, z can be anywhere between plus and minus 1. Y can be anywhere between also plus and minus 1, depending on the actual value. And so when you for example, for x equals 0 here, so that would be an example where, say, z is going to be equal to minus 1, and then expectation y is it going to be equal to 0. So in this case, for x equals 0, it's going to be actually down here. So likewise, you could just plug in the numbers there, and that would just give you the coordinates on this sphere. But all these points should be in this ring that's in the ZY plane. So is that fine for everybody?
Yes.
Yes, okay, good. All right. Then, oops. Okay, so the next one says, atom can occupy several energy states, which are denoted by E, and each of the energy states are orthogonal, like that. Energy of the 3 lowest energy states are 0, 10 to the minus 19, 3 times 10 to the minus 19. And the atom is in the unnormalized state, like this. So first one is just to normalize this state. So basically you just calculate phi and phi, and this one will be equal to 1 plus, basically you always just look at the magnitudes of these things and square it, right? So 1 plus 9 plus 16, so that is 26, right? Yeah. And so if you just divide this thing by square root of 26, then that will be a normalized state. Then find the average value of the energy of the state. So I guess, so here, I didn't really tell you what like the operator is. So normally when you take the average value, what you might be doing is doing something like evaluating this thing, right? So E, but I didn't really ever tell you what the energy like operator is. So so in this case, it actually might make a little bit more sense to revert back to the original kind of definition of like how you calculate an average, right? And remember, ultimately, when you're calculating this average, of course, it's like the probability times by the value of the energy, right? So here there's 3 values of the energy. So in this case, you can calculate the probability of each one. So the probability of each one is going to be like, so now that we've normalized this state, we can write down what the probabilities are. It's basically just the norm squared of each of these coefficients here. So we've got 3 coefficients. So the probability of the first one is 1/26. So you square it. Probability of the second one is 9/26. And probability of the third one, P2, is 16/26. So you've got the probabilities. These are the actual values. And so you just average them using those. And I think you guys can do that. Just sort of FYI, I guess. I mean, you can calculate it using the operator kind of method that I was saying. I mean, in that case, basically what this would be, I mean, it's a little bit overkill for this question because you don't really need, you know, to do it this way. It's sort of quicker to do it the way that I just showed you. But I mean, if you wanted to, you could calculate like the operator for this energy, and that would be basically the value multiplied by the state out of product of the state, like this. And then this one is 10 to the minus 19 of E1. And then this is 3 times, whoops, plus 3 times 10 to the minus 19 of E2, E2. Yeah, and so you could write this as a matrix as well if you wanted to. So basically this would be the matrix like 0, 10 to the minus 19, 3 times 10 to the 19 minus, and then all these other ones at 0. So 0, 0. And then once you've constructed that matrix, then you could just calculate it using, you know, the usual formula like this. But I think that's actually a longer way to do it for this particular question because, you know, you weren't given this observable operator in the first place. Is that fine?
Yes.
Yes, okay. All right. Then, so there's another part to this question, which is to find the variance of the energy of the state. So, I mean, again, from first principles, just, you know, what's variance? Variance is, of course, you know, it's a variance in the energy. I forget if that was my notation before, but basically it's the average of the square of the energy values minus the energy squared, average energy squared. So in this case, we've already calculated the probabilities. Now, what is E squared? Of course, E squared is just the square of these values here, right? So, so, you know, for example, so if you wanted to calculate the variance, it's going to be, so the probability 0 times by, you know, E naught 0. So in this case, this is actually just 0. So you can actually just forget about it. P1 is E1 squared and P2 of E2 squared. So this thing actually has dimensions of joules squared because it's a variance of the energy. So all these numbers should be, you know, you should get a number that's something like 10 to the minus 38 because that's the, it's kind of the order of magnitude of this thing, 10 to the minus 38 joules. Yeah. Okay. Right. Then next question, Alice has a qubit in state blah, and Bob has a qubit in state of blah. Alice makes a measurement in the plus minus y basis, and Bob makes a measurement in the, where's the rest of the question? In the 0, 1 basis, and those are the definitions of the states. Right, and then so in this case, got to write down the measurement operators for Alice and Bob. So this is basically like a measurement operator type of question. So, so Alice is in the Y basis, Bob is in 0, 1. Okay. So if you write down the measurement operators for Alice, so there's always 2 measurement operators for Alice. So, you know, we can call this first one 0. And then, you know, sorry, for 1, first one is minus Y. And then Bob is this just 0 and 1. So more or less just definition. And then B is just to evaluate these quantities here. So I think the only thing you have to be careful here is that so these are the bras of these ones, right? So that means that for example, plus Y conjugate is going to be, you got to take the complex conjugate of these values. So that's just the small trap that you need to be aware of. But so long that you're aware of that, then basically, for example, this first one, you can just look at this version of the state that we've written here, and this one would be minus I over root 2. This one would be 1 over root 2, and likewise, so this one would be minus I over root 2 again, and this one would be 1 over root 2. And then, so using the measurement operator formalism, find the probability of Alice's two measurement outcomes and Bob's measurement outcome. Yeah, so I think we've done a lot of examples of this already, but so I think what this is just trying to get you to do here, and need to look at what the wave function is. So 1 over root 3 and 2 root 2, 3, right? So for example, if you go and calculate m of like the first one times by the state, so this is plus y, and then the state is 0 over root 3 plus root 2 over 3 plus, right? Yeah, plus. Okay, and then and this is where basically, you know, you can use some of these results that you worked out in B, right? So here, this overlap that you have between plus Y and 0, that's, you already calculated that here, and this overlap in a product between plus Y and 1, you've calculated that there. So basically, you can just go and use those results. So this one, I've already forgotten what this one was. What was this one? Plus Y and 0. Sorry, what was that? So it should be minus I over root 2, right? So this one should be minus I over root 2. This is already a factor of root 3. What about this one? What's the inner product between
minus y minus?
Oh,
I think it's just 1, 2.
didn't we get minus for this one? Plus y, so we're doing, all right, yes, sorry. Yeah, sorry. I'm looking at the wrong one.
Yeah.
You're right. So you're saying it should be just this, right? Plus 1/√2,
Yeah.
right? Yep. Okay, thank you. And this one should be minus, right?
Yep.
And this one is √2, 3. Okay, and then some cancellations. Okay, so what's the simplest way to write this? I don't know, maybe, yeah, I can't think of a simpler way to write it than 1i√2 over √6 plus I plus y. Yeah. So that's the unnormalized state. And then to find the probability of that outcome on Alice, then basically we just look at kind of this number. We already know that plus y is normalized. So we just take the inner product of this state that we just calculated with itself. And this should be 1 plus 2 over 6, right? So that should be half. And I think for Bob, it's kind of something similar. So I think that part we've done many times. And then D is right, composite wave function for Alice and Bob in the measurement basis. Oh, wait a minute. Right, so Bob has a qubit in the Y state, right? Okay, so basically, okay, so minus Y state. So we just have to write down the composite wave function. So Alice's wave function was, oops. Alice's wave function was 1/√3, 0 plus √2, 3, 1. And so the composite wave function, if you've got two states, basically just take the tensor product of both of them. And this one was in the minus Y state, right? So that is just this guy up here. So I over √2 plus, oops, I forgot to write this state, plus 1/√2, this is I. Okay. And then, I mean, in principle, that's it, but it's a bit nicer to just write this out. So if you just expand this thing, then the four terms that you will get are I over √6, 0, 0, just in the usual notation where 0, 0 means 0 tends to 0. The second term is going to be 1/√6 of 0, 1. Third term will be I over √3 of 1, 0. And the fourth term will be 1/√3 of 1, 1. Okay. Oh, sorry, I didn't, sorry, that wasn't actually the question. In fact, well, maybe it's, well, okay, sorry, I didn't answer my own question properly. In fact, the question was, write it in the measurement basis, which is plus minus Y basis for Alice. Okay, so basically in this case, we've got to convert this state here into the y basis. Okay, so this goes back to the stuff that we were doing early on, where we were rewriting the state in terms of the rotated basis. This state we don't have to do so much. Well, we don't have to do anything that's written in the 0, 1 basis already. So this part is fine, but this part I should have done in the y basis. So let me just redo that. So let's see. So we first need to invert this relation here. So we need to write 0 in terms of plus and minus y. So what we can do is, for example, if we multiply this equation here by minus I here, then and then we add the 2, then this term will cancel out, right? So if you multiply this first term by minus I, then this will be plus. So basically 0 should be equal to 1 over root 2 of plus y minus y. So that's the inverted relation for 0. Then for 1, what we need to do is we need to kind of cancel out these i's on the 0 here. So what we need to do is multiply this plus y1 by I. Then this 0 term will cancel out. Then the 1's will add together to give 1. And then so we'll have minus I plus y plus minus I minus y. Okay, so now we've got the inverted relations. We can rewrite the state. So as Alice's state was this one, 1 over root 3 and square root of 2 over 3 of 1. So we can just substitute these things into here. Let me make it a bit more visible. So then when you substitute these things into here, then what we'll get is, well, 1 over root 6 of plus y minus y, and then putting the 1 into here, then well, this has an extra factor of root 2 that we've got to take care of. So it'd be minus I root 2 plus y, and yeah, root 2 of minus y. And we can just simplify this a tiny bit. So it'd be 1 over root 6 of 1 minus I root 2 plus y, and root 2 minus I minus 1. Okay, so that's Alice's state written in the y basis. And so when you write the tensor product of that with the state that Bob has, and so Bob's state was just minus y, right? So what we need to do is just take this one and then do a tensor product of this one, of this state with the state minus y. Minus y, well, it's up here. So it's 1 over root 2 I of 0 plus 1. Okay, and then you can just write that out. So it's 1 over root 12. And then we can, when you do the tensor product, you have to make sure that you don't like change the order of this one, because this one is Alice and this one is Bob, right? So if this one's Alice and Bob, then so this the first combination where we multiply this one and this one, this should be, so it's going to be like I times 1 minus I root 2 of plus y and 0. Second term, this term and this term is 1 minus I root 2 plus y and 1. The third term is going to be, so this term and this term. So it's root 2 minus I times by I of minus y and 0. And the final term is this term and this term. So that is root 2 minus I, and then minus y times 1, and then close brackets. Oh shit. Undo. Oh good, it's back. Okay, what I wanted to do is this one. I just wanted to clear this. Okay. All right. So that should be the answer when I do the composite wave function written in the y and y plus minus y basis and 0, 1 basis for Bob. Wait a minute. Sorry, I should delete another part here. This part. Okay. Right. Okay. That's fine with everybody.
Professor, I have a quick question regarding the conjugate. I just want to make sure. So the conjugate of I e to the I theta is negative I e to the negative I theta, right?
Yes. So you're just talking about complex conjugation here, right?
Yeah.
So e to the I theta, the complex conjugate of that is e to the minus I theta.
And like if I multiply I to e, like I e to the I.
Oh,
theta.
I-E. Okay.
Yeah.
Right. Okay. So well, okay. I-E, you want to do this, right?
Yeah.
Yeah.
It's
Okay.
just negative I e to the negative I theta.
That's correct. Yes.
Okay.
So yes, complex conjugation works like, so if you got like two numbers, complex conjugate, then it's equal to complex conjugate of each one. Okay, so then you just multiply the results. So in this case, what you said is exactly correct. So it's minus I times by e to the minus I theta. So basically, you know, wherever you see an I, just flip the sign. Okay. All right. All right. So, and then the final question is, so using this wave function that we just wrote down, write down the probabilities of the 4 outcomes. Okay. And then show it's consistent with B. All right. So, right. Okay. So, well, firstly, find the probability of the 4 outcomes. So for example, the probability of getting like Alice, this plus y, and Bob 0 would be, so we can call this probability of plus y 0. So that would be basically the modulus squared of this coefficient here, right? So this coefficient. So when you take modulus squared, it's going to be, okay, so 1 over 12. And then when you take modulus squared, you know, all these factors of I and stuff, like here, this I here doesn't really do anything. So it's going to be 1 plus 2. So it's 3 over 12. 3 over 12 is a quarter. And in fact, you can kind of see from each of these terms that you're going to get a quarter for each, because so for example, here, when you take the modulus here, you know, you don't, when you take the modulus, basically you're just squaring each term, and then you don't have to worry about any signs or i's or anything like that. So basically this term also is like modulus is 1. This one modulus squared is 2. So it's all these terms, it's like 1 plus 2. This one will be also 2 and 1. Modulus of I is 1. Modulus of minus I is also 1. So all these terms, basically it'll be a quarter, 3 over 12. 3 over 12 is a quarter. So question saying, sure, it's consistent with the answer in B. So I think we only did like this first one here, but what we got was, no, answer in B. I think I meant, yeah, I think I meant C. So that's typo in this question. So it must be C, right? So find the probability of Alice's 2 outcomes and then Bob's 2 outcomes. So what we found in, I think, so we only did this one, right? So Alice's 2 measurement outcomes. So what happened in C was that Alice getting this plus y state, I think we found it to be equal to a half, right? And so our probability of minus a half of minus y will be a half. And it's fairly obvious from the state. So if we just go back to what's Bob's state, Bob's state is actually this one, right? So minus y. And then if you measure in the 0, 1 basis, what is the probability of each of the outcomes going to be?
Half and half.
Exactly, yes, half and a half, because you know, each of these have you know, amplitude of, like, this is I over root 2, this is 1 over root 2. You modulus square that, it's half and a half. So basically what's going to happen is that Alice's measurement outcomes are going to be like a half and a half. Bob's measurement outcomes also half and a half. And we're going to end up with that situation that we had like in, you know, in that last composite systems one. So remember this situation where Alice and Bob, they both perform a measurement separately, right? And then basically in this example here, yeah, it's exactly actually this example. So Alice and Bob, they both perform a measurement, and then basically in this case, the resultant probabilities are like a half and a half. And then so when you look at this whole thing together as a composite measurement, then for example, the measurement probability of getting this outcome and this outcome is like a half times a half, which is a quarter. And that's exactly what we just got in the example that we just did here, but we did it more through the kind of, we just directly calculated the wave function, and then so okay, the equation is gone now, but I think you remember that the probabilities for all the 4 outcomes are half, and so basically the 2 ways that you do it, you both get like a quarter probability for each outcome either way. And so basically, you know, the task in the last part here, and question E part 2 is just to say that, well, you know, in part C, we got a half for both Alice and Bob. All the cases were probability half. And so because this is a composite measurement, so it's going to be those two multiplied, and then it agrees with the probabilities that you get just by looking at the wave function. All right. Does that make sense?
Yes.
Okay, that is good. All right, so that's well, that's that midterm. Anything else you want to go through? Homeworks. Have a look at the homeworks. So it's just mathematical preliminaries. So I think so I'll get those homework questions back to you, but right. Yeah, so you haven't really handed in these homeworks yet, but it might be actually a very good idea for you guys to, as sort of practice and also get ahead in your homeworks, I suppose, to actually go up to maybe homework 8 and make sure you can actually do all those questions, because basically that's the scope of the midterm at this point, right? So in homework, say 6, we do things like, well, there's the basis rotation stuff. So rewriting these states in terms of different bases. So that's quite an important skill you need to do. Observables. So what you'll need to do here is to basically calculate these things like these expectation values given this kind of formula, yeah, so you know, normalizing the states, so forth. Yeah, and then yeah, here's a similar kind of question to the midterm. We're sketching the states on the block sphere. So I think we did something on the block sphere in one of the lectures. Also so this is a composite system version. So if you have two composite systems, so if you combine these two states like this, then, you know, writing out the state just in terms of this tensor product, in terms of the 4 states, that's a little bit similar to the example that we just did. So in that second last question where I did it wrong the first time, where I just wrote the whole thing out in the 0-1 basis. That would be more like this question. I didn't read the question properly, so that's why I redid it and then wrote it in the plus minus y in the 0-1 basis, as the question said in the exam. But so writing it out in this composite system basis is another thing that you might want to be able to do. And then if you do a measurement in that basis, then you basically, it's just the usual rule, modulus squared of the coefficients. So even though we haven't done so much on entanglement yet, but I mean, this is, you know, you don't really need to know that it's entangled as such, but you still should be able to manipulate them and calculate things like the probabilities. So in this case, this is finding what the probabilities of measuring B in this basis is. So in this case, it's straightforward just to say that the probability of getting 0,0 is a half, probability of getting 1 is a half. And then again, here you can rewrite the basis in terms of this plus minus. So what you do here is you'd first find the inverse relation. So you invert this transformation, and then you substitute that into there, and then just factorize. Okay. Anything you want to go through at all? We've still got, well, a few minutes. Okay, well, why don't we go through, so just in this homework here, I mean, I think the kind of, we didn't, although for this last question where we write down these probabilities of B in this basis, so how about we just go through that? Because maybe we haven't really done that so much, but just so that you know, make sure you can do it. So for example, so we've got this state here, right? Well, why don't I just use whiteboard? Okay, maybe I'll slightly change the question just to make it a little bit different. Okay, so suppose further the question is like this. So we've got, say we've got this state 0, 0 plus 1, 1. Okay, so that's our state. So this is a composite system state. So 0, 0, of course, just means 0 tensor product 0 as usual. 1, 1, something similar. Now, suppose the question is rewrite this whole thing so that both Alice and Bob, so Alice is the first qubit holder, Bob is the second one. You rewrite this state in terms of the plus minus basis. And so plus minus states are defined as 0 plus 1 and 0 minus 1. Okay, so I think I've done this before already, so I won't go through it, but we can invert the transformation so that it's written like this. Okay, so you can see that if you subtract the plus and the minus states, then the first term, the 0 will cancel, and then the 1 will remain, right? Okay, so you know, if you have a single system, basically you just substitute this into the state, and then off you go with the that's your basis transformation. But what happens here? Well, maybe it's best to kind of write out this state in terms of you know, the actual meaning. So 0, 0 really means 0 tensor product 0. So then we can go and substitute the state. So it's plus state plus minus state. And let me just erase a few things here if I can. Make a bit of space. Okay. So that, and then this is tensor product with this state, 0 plus state plus minus, and then the second term similar, but there's a minus sign here. Okay, and then we can just expand everything here. So it's going to be a half, and here like you have like plus state, and so you go through all 4 combinations. So we've got plus, plus, and then second one is plus, minus, third one is minus, minus, plus, fourth one is minus, minus. Okay, so that was the first line there. Second line, kind of similar, but then there'll be some minus signs because, for example, here, this term here has a minus sign in front of it. So this will be plus, minus, this will be, minus, plus, finally, minus, minus. Okay, and then now we've got several terms which are similar here. So basically, this plus minus state, because this has a plus sign and this has a minus sign, these ones will actually cancel. These ones also will cancel. And what you'll end up with is just, right, the state, which is plus, 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 minus, minus. Actually, I forgot to normalize this state. So actually, probably what I should have done here is to multiply this whole thing by 1/√2. But what I've written is not incorrect. It's just is not a normalized state in the end. But so that's how you would do the basis transformation from this original state 0, 0, plus 1, 1 into the plus minus basis. Is that fine?
Yes.
Okay, good. All right. Well, I think if you followed all that, then you're fairly well prepared. But yeah, as I said, go through like all these homework questions and yeah, we'll go through those midterm, past midterm tests, and I think you should be in pretty good shape if you can go through all those. If you have any questions, then let me know. I'll be, I can always answer over email, or if you really need something, then happy to talk to you over Zoom. Okay, then, well, good luck on Tuesday, and I will see you then.
Yes, I see it.
Okay, finally. Wow. All right. Okay, so yeah, so I was hoping that you guys would have glanced at it beforehand, but maybe you can glance at it now. So in last year's midterm, I think the lectures weren't quite as far ahead as they are now. So I think this one only includes measurements and observables and things like that, and no composite systems. I don't think there is any composite system question. Yeah, there's none. So that's all there was for last year, but we're a bit faster this year. So I told you that anything up to and including the composite systems lecture set could be in the midterm. So given that, what would you like to go through today? Everything is easy?
Sometimes I have problems distinguishing the notations of the tensor product and just matrix multiplication.
That's totally justifiable or justified rather, because I suppose there is no difference in the notation, right? So yeah, so I guess what you're talking about is stuff like, yeah. Well, yeah, so stuff like sort of here, I suppose. Yeah, or here. I mean, I think that, you know, physicists tend to be a little bit, you know, lazy or have shorthand with notation. So in a way, I think that the way that I think of something like this is that, you know, I always know what is the identity, or like sort of not the identity, but like what is each kind of term right here. So you know, like the roles of these things in quantum mechanics are pretty fixed. As I said, even though you know, you can rewrite vectors as matrices, as we sort of kind of saw over here. So in terms of states, like, you know, that looks like a matrix, but the role that this plays is really more like a vector. And so, you know, the way you should really always think of things is that the vector states consist of vectors, and this involves a tensor product, but that basically the role of that is just to form an even bigger vector, right? So even though this one is in a, you know, say each one of these ones are like a three-dimensional system. So basically, when you combine that into the tensor product, this makes an even bigger vector. Meanwhile, things like operators, so like these measurement operators, these are, the way to think of those as these are matrices, and the tensor product 2x2 matrix, but this will be a 4x4 matrix. So I think you're right that basically a lot of the stuff is kind of not necessarily always clear by notation, like, you know, in terms of the mathematical notation, but it should be clear just from, I guess, the context of what you're doing, because, you know, the states are, you know, the things that characterize, well, the state of the system and their vectors. And then if you're like doing anything to the state, so if you're performing an operation like a measurement, or you have an observable and you have a matrix observable, then, you know, those are always matrices. So yeah, I think it could be just a matter of getting used to. So there's a long winded way of saying you have to just get used to it.
Professor, could you tell us about, like, a little bit about the process of the midterm? Like, what do you expect us to do?
Sure, yes. I mean, well, because we're remote, so what will happen is that on Monday I will, you know, we'll log into Zoom as usual, and then I will email you the midterm exam just as a PDF. So just I'll send you an email, and you'll have basically the time of the lecture, so 1 hour and, well, 15 minutes, but, you know, we might, you know, might take 5 minutes to get started, so up until the end of the lecture. And then you write your answers on a piece of paper. Please keep your Zoom cameras on for the whole duration of the midterm exam. And then at the end, when you've finished, take a picture and then email it back to me. And you know, once you've finished your exam, then you can basically just leave the Zoom session. And yes, it is a closed book test. So all you should really have in terms of answering the answering the midterm questions is just your piece of paper and a pen. You can bring a calculator, even though I don't think you would actually use it, but you can bring one anyway, scientific calculator. Okay. So, well, I don't know. No questions on the actual material? Well, the homeworks. How about the homework questions? Then why don't we then browse through the midterm exam that I just sent you?